Okay, in this presentation we're going to look at sampling distributions of sample variances and stuff like that. So there's going to be two parts to this because it's two short enough questions, so there's about 5 minutes to each. And what sort of unifies the theme of both of these is that we will be using statistical software partly to help us solve the problem. Okay, so these questions are a little bit more complicated, more complex in that respect, in that statistical software are used to solve part of the problem. So, part one, the first question is, a random sample of size 10 is taken from a normal distribution with mean mu is equal to 20 and variance equals sigma squared is equal to 1. So those are just the first two key components that we're dealing with there. Now really it's the second part there. Sigma squared is equal to 1 and that the sample size there is equal to 10. Those are the two things we note particularly. Okay. Now find the probability that the sample variance exceeds 1. That is, find the following. Probability of s squared greater than or equal to 1. Now when you're dealing with these questions here, this is the key thing, the cornerstone of almost every exercise, every answer is this stuff here. And in particular, this bit down here. The sampling distribution is characterized by this expression here. N minus 1 times s squared over sigma squared is a chi-squared random variable distributed as chi-squared with degrees of freedom n minus 1. That's the symbol there is chi-squared. I messed it up there, but it's chi-squared. Okay? Chi-square. Okay? So in this case, n is equal to 10. So n minus 1 is equal to 9. Okay? And sigma squared from the question is 1. So 10 minus 1 times s squared over 1 gives us 9s. And that is a chi-squared random variable with degrees of freedom n minus 1, which is 9. Okay? So we're already off to a good start. Probability of s greater than 1. Okay? Now, so what we're going to say here is that the probability of s squared greater than 1 is equal to the probability of chi squared greater than or equal to 9. Okay, or greater than 9. Where does that follow from? Essentially that s squared is, we're treating it as 1/9 of chi squared with degrees of freedom 9. That's gist of it. So probability of s squared greater than 1 is equal to the probability of chi squared with degrees of freedom 9 greater than 9. Basically, it's just scaling it by 9, okay? Treating it as 1/9 of chi squared. S squared is 1/9 of chi squared, if you get me. Okay, so probability of s squared greater than 1 equals probability of chi squared degrees of freedom 9 greater than 9, okay? Now this is where we use our r, okay? So this is, how do we get this? In this particular instance, what we're going to do is use r to get 0.5627. Okay, so in this case, what we're going to do here is generate, I'll show you the code actually. P chi squared, Q equals 9, degrees of freedom equals 9. That is probability of chi squared less than or equal to 9, basically. Okay, and this is the complement of that. So that is the answer there. 0.4372. Okay. The programming language R is how we would solve this one here. Now, so essentially, learning a lot of these commands here, chi squared, p chi squared, q chi squared, so on. That's how we would work with a couple of these problems here. Okay, I'm back for the second part now. I just took a pause there. A random sample of 25 recent claim amounts in a general insurance context is taken from a population that you may assume is normally distributed. In units of $1,000, the sample mean is x bar equals 9.416 and the sample standard deviation s is equal to 2.105. Calculate a 95% upper confidence limit, that is the upper limit k of confidence interval of the form 0k, for the standard deviation of the claim amount in the population. Now this is actually the trick of this question here. What exactly are we being asked? We're asked to find, now the 0 is straightforward enough. Okay, that should be a comma there. But the 0 is straightforward enough. you know, can't argue with 0. But essentially what we're asked to do is, for the sampling distribution, use the sampling distribution equations and definitions to find this value k, such that the probability of k greater than sigma, that's the standard deviation, okay, is 0.95. So this is actually just to sort of rework in the whole idea of a confidence interval here, just to sort of rework it into something that we can work with in terms of the stuff we know, like the chi-square distribution and stuff like that. Okay, now it's in terms of the standard deviation, so sigma, but we'll be working in terms of the variance soon, which is sigma squared. So just watch out for that. So let sigma squared be the population variance, okay? And remember that we are dealing with this definition here. The sampling distribution is characterized as follows. So there's 25 claims. So n is equal to 25. N minus 1 is equal to 24. Okay. Sigma squared, we don't really know what sigma squared is. Well, it's not for us to know in this particular instance, but that's distributed as a chi-square distribution with 24 degrees freedom. Okay, now this is a little bit of guile here. So what I'm going to do is start off and say that the 5% quantile for chi-squared with degrees of freedom 24 is 13.85. Okay. Now, so I'm going to use R for this particular instance, but what I'm saying here is the probability of chi-squared, I'll put in 24 there, being greater than 13.85 equals 0.95. Okay? Now, just recall that this chimes with what we're looking for up here. Okay? So, the chi-squared degrees of freedom 24, essentially what we can do there is rewrite that using the standard formula, the standard definition there, as 24 s squared over sigma squared. And that is greater than 13.85, and that's 0.95. Okay? So I hope you're still with me there. It's a little bit of a sort of bit of mental gymnastics. Okay. Now what we're going to do is algorithmically rearrange that expression there. So essentially we're just going to turn this around, swap sigma squared and 13.85. Okay. And what we do is get this probability of 24s squared divided by 13.85 greater than sigma squared equals 0.95. I think you realize we're converging to what we really need here. Okay, so let k squared be the upper bound variance of this 95% interval with 0 as the lower bound. Okay, now k squared here picked because it is variance in this particular instance. Okay, whereas we're going to switch back to standard deviations shortly, so we get the square root of that. So the probability of k squared greater than sigma squared equals 0.95. That means k squared here is using our value 24 times 2.105. Sorry, that should be squared. Okay, that's not 2 there. That should be in brackets squared. Okay, s squared. S equals 2.105 and s squared equals 2.105 squared. Very confusing typo. So 24 times 2.105 squared over 13.5. Work it out in the calculator. You get 7.678. And when you get the square root of that, you get 2.771. So the upper limit for sigma is 2.771, which is to say, oops, Skype, no Skype, $2,771 US dollars. Okay, so we can write our interval as such there. $0 to 2771. Okay, so that's the trick of that question. It takes a little bit of mental gymnastics and mental lateral thinking to work it through with it. Once you sort of go back and forth through it on your head, it works out pretty well. So we'll leave that there.